Bonjour. Bonjour. Okay, first, I would like to thank the organizing committee for giving me the opportunity to present our work here today, which is devoted to investigating the photophysics and isomerization of C11H9 cation. And well, this cation can be formed from the smallest methylated pH, methyl naphthalene. Yesterday, Karim presented that this methylated pH is proposed to be one of the responsible for the band found between 3 and 4 micrometers in the aromatic infrared spectra. But also recently, 1 and 2 cyanonaphthalene had been identified in dark clouds. The key question is, how do these species survive out there? Because, for example, in the photodissociation regions, we know that they are exposed to UV photons, so they can be ionized. And a possible scenario for these cations is to absorb another photon and then dissociate by forming a dehydrogenated cation. And it is known that this -H cation is most stable than the parent. And also it can exist in different isomeric forms. So with all this in our mind, we decided, why not? We are going to investigate the dehydrogenated cation of methyl naphthalene. In particular, we are focused on address these two questions. How fast does this cation relax, and after this relaxation, which are the long-lived isomers? To tackle this, we have used two different experimental setups, which give us access to two different time scales. In particular, Mini-Ring in Lyon and Pyrenea in Toulouse. So let us start from the end of this story, which are the long-lived isomers of this cation. Well, here we can see a scheme of this setup. Its soul is a Fourier transform ion cyclotron resonance cell, which has good isolation conditions, so we can access long time scale. In these experiments, for producing the cations, the first step is to admit the neutral molecules into the cell directly. Then we can irradiate it with a 266 nanometer laser, producing thus different cations, including the -8. After that, we can isolate the -8 cation. And now we can play, because by using an OPO laser, we can investigate the fragmentation yield as a function of the wavelength and irradiation time. And in this presentation, I will focus on two representative results for two different wavelengths, where here we are observing the normalized fragmentation yield, that is population, as a function of irradiation time. And well, we found that for the highest wavelength, after a given irradiation time, the population of the parent remains constant. So at least one isomer doesn't absorb here. But also, for both cases, we observe one fast decay and at least one slow decay. So we can assume that each of these decays is related with one different isomer. By considering all this, now we can rationalize that at least 3 isomers are present. And with this, we can fit our curves with a 3-decay model. And one of the purposes for doing this is to obtain the population of these three unknown isomers. So let's call them A, B, and C so far. And well, we did this for different wavelengths, but also by using two different precursors to form the C11H9 cation, one methyl naphthalene and two methyl naphthalene. And it is interesting because for C isomer population, we found around the same value, where for the other two, we have a slight differences. But well, now let's continue because we want to put face to these isomers. So to do so, we performed this other experiment. Now again, we produce our -8 cation, we radiate it during a given time, but now we isolate the remaining population after irradiation, and we admit the neutral precursor into the cell to investigate how these remaining cations interact with the neutral molecules. And here we can observe the obtaining results for the two main channels observed. No reaction or reaction by adding a CH2 group. And well, it's beautiful because we have a completely different story for both wavelengths. Where for the highest, the remaining population after 300 seconds of irradiation doesn't react. For the lowest wavelength, the population react. And now, if we consider what is well known for toluene -8 cation reacting with toluene, that is, benzyllium isomer reacts by following this reaction by adding a CH2 group, where tropylium doesn't, we can finally put face to our unknown isomers, which are A, 2-naphthylmethylium, B, 1-naphthylmethylium, and C, naphthyltropylium. And also, we can provide populations for these isomers, around 30% for naphthyltropylium, and the remaining 70% for both naphthylmethylium. And this is interesting because each isomer will give rise to different chemistry. But also, before us, Wenzel et al. Investigated the long-lived isomers of this cation. They found similar population. And what makes this really interesting is the fact that they produced the -8 cation with a completely different way, by collision between electrons and the neutral precursor. And these results would suggest that the population of the long-lived isomers is independent on how the cation is formed. Out there, we can find a lot of different ways for producing cations. But well, now let's move to the beginning of this story. How fast does this cation relax, and which are the mechanisms behind this? Now here we can see the other setup, mini ring. And this setup is an electrostatic storage ring. And due to its small size, it's for that, mini, we can access short time scale just after cations formation. Well, now in this experiment, we produce the cations in a completely different way because we use a plasma source. So a broad internal energy distribution is expected even for the -8 fragment. Well, after formation, we can select the -8 cations by using a magnetic sensor. And they go into the ring, where we measure the neutrals formed in two different points. And now, regarding the relaxation dynamics, first, natural decay takes place. It is a spontaneous decay due to mainly dissociation event. But after that, we don't know what is going on. So we use photons as a probe to re-excite these cations and to investigate other mechanisms competing with dissociation. And we can do this in two different time scales. The first is millisecond, because first we have the storage time. This total time the cations are inside this ring. And during this time, we shot a laser during 10 times. So now if we zoom in, if one of these lasers shot, we observe this. So we can define the second time, T prime, which is the time just after laser fire. And now here, if we integrate each of these peaks, we can investigate what is going on in the microsecond scale. Here we are observing this plot in log-log scale. We have a kind of linear trend, let's say. So a first approach for obtaining qualitative information is to fit the experimental decay with a power law, T minus alpha. And well, we found that this parameter decreases as the storage time increases. And this means that the internal energy distribution is changing with time. But we also found that the experimental decay deviates from the power law. And well, to try to understand what this could mean, let me introduce to you these two string cases for the internal energy distribution. Well, in one extreme, imagine that we have a well-defined energy, that is a delta function. So in this case, we should observe a pure exponential decay for our neutral yield as a function of T prime, if only dissociation is active. On the other extreme, imagine that now we have a kind of infinitely broad internal energy distribution. So we would have a lot of exponential decay. And if we sum up all this decay in a log-log plot, we could observe that the T-1 function fits these results, if only dissociation is active. So if we consider that our internal energy distribution is broad enough, any deviation for longer times suggests that something is going on beyond dissociation. And well, so far regarding these results, because we are still working on it, we can say, how fast? Well, there is cooling, but we know that the relaxation mechanism of this cation is slower than observed for very similar molecules of naphthalene or azulene. Also, we know that dissociation is being quenched in the 100 millisecond range. Due to the time scale, we have two possible candidates, recurrent fluorescence and or isomerization. And well, to finish, to say that all this work had been done within the SIMPA-COOL project, which aims is to investigate the relaxation dynamics of astro-pH. And well, we are going to couple a copy of this mini ring setup, but with cryogenic condition, to the VUV beamline at Soleil. And with this, we will be able, first, to mimic in a better way the conditions found in the photodissociation region, and also to access longer time scale, for example, to investigate the role of infrared relaxation. And finally, we will be able to provide experimental dissociation and recurrent fluorescent rates. And this is really important, as had been discussed, because first, there is an important lag for these rates, and also they are mandatory for modeling. So let's see. And finally, I would like to thank my team, because together everyone achieves more. And of course, thanks for your attention.